Welcome to This Explainer. Today, we're diving deep into the microscopic, completely invisible processes, and honestly, the massive macro-scale power of the Linux server. I am so glad you're here, because we're going to take something that most people just picture as a glowing box sitting in some freezing cold data center, and we're going to reveal the absolute magic happening inside of it. I mean, think about it for a second. Every single time you click a link or tap an app on your phone, you are instantly triggering this massive chain reaction that you can't even see. To us, it feels instantaneous, right? Boom, the page is there. But the reality? It's a high-speed, incredibly coordinated dance of hardware and software. To really ground this tech in reality, consider that almost every daily digital action you take relies on a Linux server running quietly in the background. Whether you're binge-watching YouTube, aimlessly scrolling Facebook, checking your bank balance, or just, ordering some takeout on a Friday night. Behind almost all of those seamless experiences is a Linux server just working overtime. So today, we're going to map out exactly how this works. We'll start by understanding Linux servers, look at what happens during boot, walk through a complete web request, uncover the secret of concurrent connections, explore the keys to server stability, and wrap up with the ultimate weapon, automation. Let's get right into it. Section 1. Understanding Linux servers. What are we actually talking about here? Let's start by totally busting a major misconception. A lot of folks just assume a Linux server is a regular computer that's missing a monitor. Just a black screen with some scrolling green text. But it's way more powerful than that. It's a highly specialized operating system built from the ground up, specifically for server operation. Its whole purpose in life is to manage the CPU, the memory, the hard disks, and the network interfaces with absolute ruthless efficiency. At the absolute center of all this is the Linux kernel. You can picture the kernel as the central control system of a massive, bustling city. Actually, scratch that. It's the literal brain of the entire data center. Without the kernel directing traffic, managing resources, and telling the hardware exactly what to do, the whole city would instantly fall into complete gridlock. Moving to Section 2, what happens during boot? Let's see how this brain actually wakes up. Waking up happens in 4 highly structured steps. First, the BIOS or UEFI runs a power-on self-test, or post. It's basically yelling out, "Hey, CPU, RAM, disk, are you guys alive?" Once they confirm, we hit Step 2. The bootloader kicks in and executes something called grub. Step 3 is the kernel boot, where that city control system we just talked about takes over the hardware. And finally, Step 4. Systemd fires up all your essential services, like Secure Shell for remote access, web servers, and databases. I absolutely love this analogy for Step 2. Grub, that bootloader, acts exactly like a control tower on a busy airport runway. See, the computer hardware is fueled up and ready to fly, but it has no idea where the pilot, the Linux kernel, is actually hiding on the hard drive. Grub is that control tower, safely guiding the system right to the kernel so it can take off. All right, Section 3. The complete web request process. How it handles your demands. The server is awake, so how does it handle your request to load a web page? This microscopic journey takes less than a single second, which is mind-blowing. First, a DNS query finds the actual IP address. Second, a TCP connection does its reliable 3-way handshake. Third, your data packet hits the Linux kernel, checking the firewall and finding the right socket. Fourth, a web server like Nginx or Apache grabs it and parses your HTTP request. Fifth, it gets handed off to backend processing, maybe some Python code, checking a database. And finally, Step 6, the data is packaged into an HTTP response and blasted right back to your screen. 6 insane steps, literally in the blink of an eye. Section 4, the secret of concurrent connections. What happens when things get crazy? Now, handling one request in under a second, great, we expect that. But what happens when 50,000 users hit the server at the exact same millisecond? The secret to surviving that isn't just raw horsepower, it's multitasking. And that's managed by this brilliant piece of the kernel called the scheduler. Its sole job is to rapidly decide who gets to use the CPU first. When you've got thousands of threads begging for attention, the scheduler is the ultimate judge. Think of it like a highly efficient traffic cop on a massive 10-lane highway. The scheduler prevents data pileups. It gives a tiny fraction of a millisecond to one task, switches to another, and then another. So unbelievably fast that to us, it looks like the server is doing everything simultaneously. It keeps the whole system flowing without crashing. But that traffic cop has some serious backup. This control is heavily supported by advanced memory management. Linux squeezes every ounce of efficiency out of the hardware. It uses virtual memory to give programs the illusion that they have their own massive RAM space. It uses page caching to keep frequently used files ready to go instantly. It uses swap space on the hard drive as a safety net if RAM gets full. And it uses NUMA architecture to optimize how memory talks to multi-core processors. It is incredibly slick.
Moving on to Section 5, the key to server stability.
When we zoom out to the enterprise level, the goal totally shifts. It's not just about pure speed anymore. It's about absolute, unbreakable endurance. Linux completely dominates global data centers because of 3 pillars of stability. First, strict permission control. By locking down user and group limits, a rogue app can't take down the core system. Second, service isolation. Using stuff like Docker and containers, applications are walled off. If one program completely crashes, the rest of the machine just keeps humming along. And third, comprehensive logging. Linux obsessively records everything, so if a bug does pop up, engineers have an exact trail of breadcrumbs to fix it instantly. Finally, Section 6, the ultimate weapon, automation.
Okay, we've got a stable, isolated server. But how do we manage the entire global cloud? Well, here is the absolute crucial realization you need to take away from this explainer visual. Screens, graphical interfaces with all those windows and buttons, they actually limit you. If you have to physically click a button, you can only work as fast as your hand moves a mouse. True, frightening power comes from the command line interface, the CLI, and automation.
This is where things get wild. Using automation tools like Bash scripting, Python, Ansible, Terraform, or Kubernetes completely changes the game. An engineer isn't logging into one server at a time anymore. Through the command line, one single engineer can simultaneously update or configure tens of thousands of Linux servers all over the globe, using just a few lines of code. It's basically magic, and it's why the entire cloud runs on Linux.
So let's tie this whole shebang together. The next time you sit down, grab your coffee, and load up a simple web page, remember what's actually happening. You aren't just looking at text and images. You're looking at the synchronized result of thousands of invisible components. The Linux kernel, TCP/IP protocols, lightning-fast web servers, massive databases, containers, and global infrastructure, all working in perfect microscopic harmony. And orchestrating all of it, the invisible brain of the internet, Linux.
But hold on, we've only cracked the server side of the equation today. What actually happens out there in that vast, chaotic web of fiber optic cables and routers? The network journey is just as wild, if not wilder. How exactly does your request travel across oceans in mere milliseconds? Well, make sure you catch our next explainer to find out exactly what happens out on the open internet the exact moment you hit enter. Thanks so much for joining me on this deep dive, and keep asking questions.